in the spirit of this course, that is not getting into the details of finite element method, but at the same time does not want to leave everything as complete black box for those interested in modeling, here is some discussion on higher order elements. So here is a very simple sort of introduction to what is meant by higher order element and why that might improve our computation. Okay, so let's say we have a function like this. So let's say it's temperature versus position, and the true solution, this is my true solution, looks like this. But let's say I am doing finite element and I have a very simple computation where I have two elements. Okay, so this is one element and this is another element. So element 1 and element 2. So if I do the computation, remember computation is always done at the nodes, and so my computed value could look something like this. The temperature here, and I calculate here, and I calculate here, let's say. Okay, and then in between those points, of course, I can only do a linear interpolation because my calculations are only done at the nodes, and there is no other way to interpolate between just 2 point values. So this is going to be a FEM solution, a finite element solution. Okay, so now suppose I add more nodes to this element. So it will still be two it will still be two elements, but each element will now have an extra node, let's say in the middle. Okay, now what will happen is my computation would happen here, 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 here. So this will give me some added degrees of freedom, more flexibility in trying to match the true solution. So now the solution might look something like so. If I join now using this point as one of the points in the interpolation process, and it's a we can do this in a quadratic way. So you can see now this is improved solution, okay, using extra node in the element. So the extra node in the element makes it what we are calling higher order element. We'll see how we do it. So just remember that we are not adding elements. We have the same number of elements, 1 and 2, but now it's a 3-noded element, 3-noded element. So a 3-noded element, again to repeat, kind of gives an extra point for interpolation, and the interpolation is better, and it generally would be improving and going closer to the true solution. That's the whole idea of higher order elements. Recap, when we had two noded elements, temperatures at points other than the nodes were given by an equation like this, right? So if it is a two noded element, then temperatures at the left node could be TL, here it could be TR, and any point in between we get it by linear interpolation. And so that's this equation. This is the equation that gives a weighted combination of left and right depending on where you are. So these PL are these which are the interpolation functions. This is PL and this is PR. So notice that PL, if I plot it at z equal to L, so this end is L and this end is R, at z equal to L, this first one is 1, and then at z equal to R, PL is 0. So PL goes from 1 to 0, and then PR goes from z equal to L gives me 0, and z equal to R gives me 1. So PR goes from 0 to 1. So these PL and PR are my interpolation functions, but they are also called, PL, PR are also called shape functions. Shape functions, okay? So this is the nature of doing the 2D problem. I mean a two-noded element. Now we want to see what happens for a three-noded element. So this is still one element, but it has three nodes. Following the discussion that we just had in the previous slide, for a three-noded element with this extra point in between, we can do a better job of interpolation. Okay, so let's write down the equations for interpolation. Now, the general form of writing the interpolation equation is like this. T is a combination of these polynomials and the values at the nodes. You notice that this is consistent with what we did for 2D. But here, the interpolation functions are given in general as a multiplier of this quantity. And all this is kind of hard to see. So let's write it down for this one element that is three-noded. Node 1, node 2, node 3. And I'm going to now write up this equation for the three-noded element. It's the interpolation of the values at the nodes to get any other value in between. So if I use this formula, you notice it has a summation, so there will be three terms for 1, 2, and 3. So let's write the first one. So first one would be P1Z. So P1 from here is going to be Z minus Z2 over Z1 minus Z2. So I is 1 and K cannot be 1, so it's 2 and 3. So there will be two terms because of the multiplier. Okay, Z minus Z3 over Z1 minus Z3 times T1 bar. Plus, I do the same thing this time for I equal to 2 And so you will get this expression following the same process. I'm just putting in I equal to 2, so k can be 1 or 3. So z minus z3 over z2 minus z3 times t2 bar plus z minus z1 over z3 minus z1 times z minus z2 over z3 minus z2 t3 bar. Okay, so I want you to see, even though it looks so much involved, but it has the same format as this guy here. Okay, so what is the difference? The difference is, instead of the function, the interpolation function being linear, here it's quadratic, because if you multiply these two terms, you get z square minus z2 plus z3 times z plus z2 z3. So it has a square term, so it's a quadratic interpolation. That's the difference. Otherwise, it has the same kind of format as this one. Now, if you recall how we got the finite element equations, so at the end, those linear, those set of equations, how we got them was we put this linear interpolation for 2D in back to the equation, and we minimize the error. So we do the same thing now. We plug in all of this into the my governing equation, which is this one, and then minimize the error to get the final equations. So that will be a humongous amount of algebra, but it is the same process. Now we can go to even higher order element. So we can have the same element and have two more nodes in between. Okay, and so if we do that, then we are going to again write down in terms of 4 terms: t1, t2, t3, t4. Okay, so that would be an even higher order element, as we say. So this is linear or first order. This is the quadratic or second order, and so on. And this is the third order, okay, or cubic element. So again, you plug that in and you develop finite element equations. So in a software such as COMSOL, it has done all of these algebra and it has pre-programmed. So as soon as you choose this with third order element, which we almost never use, it uses those equations. So it's able to go easily from a linear to a quadratic and so on. Okay, so we want to try out the discussions that we just had for 2-noded element versus a 3-noded element on a real computation. Okay, so let's first define the problem. So the problem is heat conduction in a slab, something that we have been doing. So my governing equation is del T is equal to alpha del square T del Z square, where Z is this dimension, and we have an initial temperature Ti, and then the surroundings is T infinity. So T infinity, and so the surface temperature, which is higher than Ti, so the surface temperature would keep increasing, and we would have a solution at some point in time. We're going to have a solution that looks like this at any given time. So this is my expected solution. Okay, so, and then this is my surface temperature. So we're going to solve this problem in two ways. In both cases, we will have two elements. So two elements meaning this distance, we divide it into two parts. And so we have element 1 and element 2. So on the plot, I'll just enlarge this. So we have element 1 and element 2. Okay. And here also we have element 1 and element 2. Okay. So what's the difference between the two? On the left, I'll consider two noded linear elements, two noded elements. So these elements will just have two nodes. Each one will have two nodes. So for example, one has these two. Whereas on the right, I'm going to consider three noded quadratic element or three noded element. So here I have this with another node in the middle. So this is my one element, okay? And so now let's do the computation here, and let's see how it goes with time. So with time, temperature increases. If I stop for a second, then you can see the expected temperature profile makes sense, because the entire region is divided into two elements. And so for every element, I have the nodal temperature that we calculate, and every point in between we interpolate, right? Same here. So the nodal, two nodal temperatures, and then every point into, and because it's just the 2 points at the end, I can only interpolate linearly. So that's why we have two straight lines as the solution here. And if you keep it going, then with time, the temperature increases everywhere, which makes sense. So it's not qualitatively, it's not wrong. It's okay. But let's see how it looks on the one on the right-hand side. So here, as you can see, it's also calculating temperatures, and temperatures are increasing, like in the left-hand side. And if we can stop here, yeah. And then, so the big difference that you see is because we had the extra point in between the two nodes in the element, the extra node, okay, it allowed the interpolation as a quadratic and not as just a line, because of this extra degree of freedom. And so because of that, the solution is smoother, and it's also closer to, it is most likely closer to the true solution most likely. Why? Because in this case, there's one reason, one physical reason I can give, is there's no reason for the slope here to suddenly change. If the slope changes, that means the heat flux changes, right? Heat flux is Q double prime is minus K del T del X. If the slope changes, then the heat flux changes. Why would heat flux suddenly change at this point? It's really an artifact because all we have is a linear interpolation between them. And so here, on the other hand, you can see the solution is quite smooth, and by having this extra node, it allowed more degrees of freedom, better ways to try to fit the true solution, and it is really most likely closer to the true solution. Now, this does not come at zero cost. So realize that in this case, on the right-hand side, we now have 5 nodes instead of 3 before. So, which means we are doing close to twice the computation. So the computation increases, but we are getting closer, most likely, to the true solution. Another way to increase the accuracy would be to have more elements, okay, instead of higher order. So these are still 2-noded elements, but now they're just they're just 2-noded elements. So that's another way to increase, instead of going to 3-noded quadratic elements. Which one works the best for a given situation? It's hard to say, okay? But it's important to know that as we put in the extra node for the extra interpolation, we can get to the true solution probably faster, easier, but it is at an additional computing cost. How the implementation goes in a particular software, what button to click to choose a particular type of element, that of course depends on the software, but I just want to share with you how we do this in COMSOL, which is one of the softwares we use. And first you have to turn on discretization. So if you click on this arrow, then you have to actually check discretization before you can see, because this is not something we need to play with normally. We don't play with the element types, higher order elements, very often. Once we have checked this one, then in the model builder for the particular physics, which happens to be heat transfer in this case, if you go to discretization, which is below equation and physical model, ambient setting, and all of that, if you go to discretization, you notice that quadratic is selected. So that is the default for this physics, heat transfer. And that from their experience, they know this works, and so they have already set it as default. If you click here, then you get all of these choices of the type. Remember, we talked about linear and quadratic, and also cubic, which would be cubic would be like this. So 2 more points inside. Okay. to summarize then, we did our entire finite element development earlier with a line element. Okay, line element that has two nodes, and you interpolate all values in between. What we just talked about is in this one element, if I add another node, okay, so a third node, it allows to do not just a linear but a quadratic or a quadratic interpolation, or fitting a curve, not just a line. And that makes it easier to get to the true solution. And it just gives us an added sort of degree of freedom to be able to try to match the solution. So if we do this, the discretization error, which we will discuss later, but you can just think of error, is likely to decrease for this kind of error. So likely lower error. Okay. So all that is for line elements in 1D. And the same thing can happen in 2D. So this is 1D, 2D, and 3D. So in 2D, for example, instead of the 3-noded triangle, I can have 6-noded triangle. And so that will give me more degrees of freedom and an easier way to match the true solution. But of course, there's no free lunch. This comes at a cost. We are adding another node in this case, and 3 nodes in this case. All of those nodes are being added. So for example, in this one, in the case of 1D, I am adding another node, meaning I'm almost increasing the number of nodes by approximately 50%. So the computation cost is going to increase. And so one could think that, okay, I can also, instead of making it a 3-noded element, I can also make 2 elements, meaning I can make the element smaller. So now this is 2 elements. So that should also help. So which direction should we go in a particular situation? This is very far from obvious. Should we go for a higher order element, or simply more element? So more or higher order element. Say same thing here. So in a complex computation, it is very far from obvious which way to go, and there are some general guidelines, but these are based on practical experiences, and these guidelines are typically available in the software user group blogs.